Continuing in this series of videos, taking a look at Professor Lewin's interpretation of physics and adding what critique or observations I have to offer and such. And so let's get on with the show. He did preface this lecture. He had sent out some sort of review things, I don't know, cards for people to fill out about what they like or dislike, and he was talking about some of that. So I skipped some of that, and we'll just get to where he should be starting to talk about physics a little bit. Some of that conversation here, though.
It here was extremely simple. Conceptually, they were not so simple. But from a math point of view, trivial. Clearly, I cannot cover all the subjects in a 50-minute exam. I have to make a choice. So your preferred topic may not be there. Some of you think that the pace of this course is too slow. Some of you think it's too fast. The score, the average score was 3.8. 4.0 would have been ideal. What do you want me to do? I can't accommodate all of you, those who...
Well, you asked for complaints and then they complained. So, you know, you get what you get.
Think it's too slow, and those who think it's too fast. 3.8 is close enough to ideal for me, 4.0. And so I'll have to leave it the way it is. Besides that, keep in mind, you are now at MIT. You're no longer in high school. Now,
Right, so you know, I just always add this context. So they've had 100 years to refine this theory. You know, lots of little contributions, different people, Faraday lens, this. And still, they have to resort to, you know, some cheats to make it logical, like putting that millimeter space between the jar.
good news. There were quite a few students who said the homework is too long. Not a single person said it was too short. I can fix that. I will reduce all future assignments by about 25%, effective tomorrow. I have already taken off assignment number 5, 2 problems. You're down now to 7. And I will do that, all assignments that are coming up. My pleasure.
Anyway, yes, sorry, I thought I had cut off the parts where, you know.
Today, I'm going to cover with you something that conceptually is the most difficult of all of 802. And you will need time to digest it. And if you think that what you're going to see is crazy, then you're not alone. The only good news is that conceptually, it's not going to become more difficult. Remember...
All right, so they're conceding that their understanding is insufficient, and yet they won't concede that their underlying theory is incomplete.
That Ørsted in 1819 discovered that a steady current produces a steady magnetic field, and that connected electricity with magnetism. A little later, Faraday therefore suggested that maybe a steady magnetic field produces a steady current. And he did many experiments.
All right, so a lot of this just has to do with the fact that, look, we know the force changes a substance. So as you bring two things together, if one thing is projecting something other than a mixture, that it's filtering the force, that filtered effect is going to hit the other thing. And that filtered effect has an impact on the other thing. That is, it pushes electrons in one direction and it pushes protons in the other direction, you know, depending on what's being filtered. And in doing that pushing in a direction, that can cause pressure. So that can make the atom ionized, essentially. It can make the atom polar. And it can make it polar in two different ways. It can make it a completely charged atom, in the sense that from any direction it appears to be positive or negative, or it can turn into a dipole, which means it has a side that's more positive and a side that's more negative. And depending on what effect it causes in the other thing is going to create a force, because it's now a filter. And so depending on how much of it gets changed, it's going to filter what sends back to the other guy. And you have this induced struggle between identity in terms of the two things will start to influence each other. Then the rest is just theory about how it moves through conductors or insulators. So that's how I would summarize.
To show that turned out not to be so. And one way he tried that is as follows. He had here a battery with a switch, and here he had a solenoid. He closes the switch, the current will flow, and that creates...
Fantastic drawing. I really just, very well done.
A magnetic field in the solenoid, and that magnetic field, maybe it runs like so. Depends on the direction of the current.
So again, the running part is kind of iffy. Obviously the coil of the wire, the pressure is going to be moving through the wire in a sense, migrating from atom to atom to atom, which means essentially the little magnets are going to be moving perceptually inside the coil. There's going to be a moving magnetic field because the atoms getting polarized are switching on and off, on and off, on and off, and that creates a pattern, like a wave. A wave of pressure. But the real force is a radial force being excreted by the wires. The wires are filtering gravity and changing, just as we are affected by the change caused by the other half of the earth, changing the world we live in.
And so now he put around this solenoid a loop. Let's call this loop number 2. It was around the solenoid, and let's call this loop number 1, of which the solenoid is part. Whenever there was a current in number 1, he never managed to see a current in number 2. If there's a current going in number 1, there is a magnetic field. And that magnetic field is seen, of course, by the conductor number 2, by that loop.
Alright, so the thing is here that with a DC current, you do this and you turn the power on, there's a current in number 2 for the moment while the pressure moves. And as soon as the pressure is equalized, as soon as it reaches its equilibrium, there's no more change in current to loop. And I would argue that's because it also pressurizes, and that's the end. Especially in a loop, it's pressurizing one end and the other end. And so until the field collapses and allows the pressure to move back to the rest of the wire's essentially been polarized. One end is going to be negative, one end is going to be positive in terms of the pressure, and that can't change until you turn the electricity off and allow the pressure through the conductor to reconduct, to move, migrate back through the entire wire, and then you can move it again. But you can't move it once you've moved it, pressurize something. There's a certain amount of pressure, and that's it. Can't create any more, can't pressurize it more, so you're just stuck with the pressure stuck, and everything just freezes until you allow it to relax. So that's why you need an alternating current to maintain a current in the second wire, is because you need the pressure to relax.
For any current. So he concluded that a steady magnetic field, as produced by the solenoid, circuit 1, does not produce a steady current in number 2. But then...
So, again, it sort of would if you allowed the pressure in number 2 to go somewhere. It's a closed loop. The pressure gets pushed to the end where there's no magnetic field. There's a difference between the pressure of the wire that's in the field and the pressure of the wire that's not in the field. And unless you create some mechanism where that pressure can get to ground, there won't be any continuous repressurization. And obviously if you let it go to ground, the amount of pressure would be so minor that you couldn't collect the current anyway. Because you're still not going to be able to pressurize, you're still not going to be able to put the high pressure back in the wire part that's around the coil. You can't repressurize that part, and that's the part that needs something to push. So if you've pushed all the pushables, let's just say there's two things, pushables and non-pushables. You pushed all the pushables out of one section of the wire. How do they get back? So if there's no way for them to get back, you can't push anything. There's nothing to push. You push all the pushables out. Even if I tie it to ground, you got no pushables.
One day, he noticed that as he closed the switch, he saw a current in number 2. And when he opened the switch, again he saw a current in number 2.
Right, reverse current. So one current goes forward, the pressure moves in one direction, and then you turn off the juice and the pressure moves back in the other direction. Kind of logical.
And therefore he now concluded that a changing magnetic field is causing a current. Not a steady magnetic field, but a changing magnetic field. And this was a profound discovery.
Right, so now they've interpreted that to mean, he often uses this term that the field fights back, or the thing fights back. It's not really fighting back. It's just the facts that, there's this circumstance of where the pressure is, and if you provide a place for pressure to go back, it'll go back. And the fact that also that you're always going to create the inverse magnet when you are pushing something, another magnet. When you're imposing the force, which you'll impose will be a reciprocal of you, the opposite, sort of. If you have your protons end showing, your butt end showing, the head end showing will be what you'll produce in something else.
Which changed our world, and it contributed largely to the technological revolution of the late 19th and early 20th century. A current, therefore...
I sort of don't like his little... He puts in these little bits of, like, patriotism or something. I don't even know what to call them. Little bits of cliche, this is what made America, or some kind of bullshit. And it's just, unnecessary. Whatever that's called. Political blah blah.
An electric field can be produced by a changing magnetic field. And that phenomenon is called electromagnetic induction. And that phenomenon runs our economy, as you will see in the next few lectures. I have here a conducting wire, square. I could have chosen any other shape. Try to make you see three-dimensionally. And I approach this conducting wire with a bar magnet. The bar magnet has a magnetic field running like so.
Alright, so again he's this field thing, okay, with the arrows. Now, it's fine, we will say that the arrows are always coming out of the north end of a magnet, so we have some way of recognizing north from south and the two different effects. So this is electron pressure is being pushed onto something, which means that it's going to push the electrons away and the protons will drift in the opposite direction, or tend to. It's because it's the north end of the magnet in this case, it will tend to pressurize atoms. That is, atoms will absorb, the electrons will absorb the pressure. So say that's a ball and it's going to get rained on with this little bit of extra electron force. The electrons getting hit on the one side of the atom are going to gain some of that pressure and create more pressure in the atom, and as I've sort of indicated, in doing so will change their polarity and change their charge in the sense that they'll go positive because the atom might expand a little bit, meaning that the nucleus will be more exposed, and so it'll charge the atoms and create more energy in them, and the vice versa. If the south end, you shrink the atoms and create less energy in them, and you also have the situation where if there happens to be any dipoles, the dipoles will line up in the opposite direction to the magnetism you're exposing the surface to.
As I approach that loop, that conducting wire, moving the bar magnet, that's essential. I can't hold it still, I have to move it. If I come down from above and I move it down, you're going to see a current going through this loop.
So what the loop is going to do is it's obviously going to push the negative pressure to the outside of the wire, and the inside of the wire will become low pressure, or north-south. And again, the pressure doesn't have anywhere to go in this circumstance, so it's all going to push to the outside of the wire. There's going to be some movement through that process, and then the movement's going to stop when the magnet stops. So as soon as you stop pressurizing the system, it'll stop doing anything. But the idea that there is a current flowing in any direction here is just wrong. If I put a voltmeter on here, I break this wire, the wire will still have the pressure in it at any point, and I could measure that pressure that you're producing in the wire by pushing the magnet into the wire. But I can also just drain that pressure. But again, until you relax the wire again, there's no way for the pressure to get back into the wire. So until I take the magnet out, I'm going to be done. So unless I have to move the magnet away, or I have to expose the south end, I have to do something to allow the pressure to get back into the wire.
And that current will go into such a direction that it opposes the change of the magnetic field. The magnetic field is in down direction and it is increasing as I move the bar magnet in. Then this current loop will produce a magnetic field which is in this direction. And when you look from below, the current will go clockwise, producing a magnetic field in this.
So this is an opposing magnetic field. And it's opposing because of the point that the outside of the wire is now the most pressurized. I mean, the electrons have gone that way, and if they've been pressurized, and so the magnets are essentially pointed with their just again, you have to think about it. The north ends, that wouldn't produce the right polarization. So you always have to think through these things. So at the moment, I'll just leave it. But so this is there's two circumstances. In most cases, you get the field created is the opposite field in the sense that it's the attractive field. In this case, he's describing a repulsion that's being created. You know, the B field is in the opposite direction. He didn't assign a value to it, and he has it going clockwise. I mean counterclockwise. So counterclockwise means the B field is actually positive. So it's an attractive force.
Direction.
I mean, if it was going clockwise, then the B field going up would be the north end of the magnet. So because he's going counterclockwise, the B field has to be the south end. See, this is where this would be so much clearer, I think, if the B field was assigned its value, positive or negative, and we didn't have to bother looking to see which way it was going. I don't understand why they're using a term B to describe something that can be north or south.
If you move the bar magnet out, then the magnetic field is going down here, then the current will reverse. The current wants to oppose the change in the magnetic field. And that's called Lenz's law.
Okay, so the current wants to oppose. So this, the first point I would say is what's causing the current. And what's causing the current is the pressure being created, the change being created when you're making the atoms into monopoles and dipoles. So as you're turning them into charge and magnetism, that's what's creating all the other effects. So any current effect, that is differentials in pressure along the wire, is entirely the consequence of the fact that you have magnetized the atoms. So that's what comes first. The current's not opposing something. the magnetization of the substance is causing a pressure differential that you can measure. But the current doesn't come first. The current is a consequence, a byproduct of magnetizing the substance, and it isn't a conductor to the same truth. As you pressurize the atoms by moving electricity through them, all right, as you charge them, that's all that's moving really, is that charge. So this atom gets charged, the atom next to it is not charged, so it hits it and passes on its charge and passes on its charge. That's the movement of the current. But what causes it is, first you have to be charging the atoms. First you're creating the magnetic monopoles and dipoles. That's causing the current, not the other way around.
Law. It is the most human law in physics, because there's inertia in all of us. We all fight change at some level.
So again, he's saying it's fighting change. No, it's a byproduct of change. It's not fighting change. Change happens first, and then it has a consequence. So it's just a misordering of the events.
This law is extremely powerful in always determining in which direction these induced currents will run. It is not a quantitative law. You cannot calculate how strong the current will be. But it's very useful, as you will see today, to know the direction of that current. That gets you out of all kinds of problems with minus signs. I now want to do a demonstration.
I guess it would be better if you first fixed plus and minus to make it match the actual truth of the extra electron pressure that you're creating. And then if you assigned your variables that have two states, B field plus, B field minus, if you just assign them one of those plus and minus signs, then I guess you'd solve all these plus and minus problems.
Which is very much like what you see here. I have here a loop. That is the square that you see there, except that it's not one loop, but it is many of them. Hundreds.
So again, magnifying whatever effect you have by first putting the wires right next to each other, which means anything that happens in one wire is going to be imposed on all the other wires. And also the inside is going to be full of the field. The changes created by each wire are going to just be magnified in that space.
Matter. And what we're going to show you is an ammeter that is connected. So there's somewhere in this circuit an ammeter. I have a bar magnet, and I'm going to approach this conducting loop with the bar magnet. And you're going to see a current running in one direction, and when I pull it out, it will be running in the opposite direction. And when I hold my hand still, so that the magnetic field is not changing, no current. You're going to see the current meter there. And here is my bar magnet. I come close to this conducting loop. Notice, you see a current. I pull back, current is in the other direction. Now I will go faster, so that it...
Alright, so again, it's more of a voltage measurement than a current measurement, but whatever. When he moves the magnet, the very fact that the speed at which you move it changes the deflection is sort of an indication that, in my opinion, that it takes time for these atoms to pressurize and to polarize, and that it matters how fast you move the magnet because that's a factor in how much pressure there is. So obviously the magnet has a density of its magnetism, so much it's going to be hitting it with extra amounts of something, and the faster you move it, the more stuff per second is going to be hitting those electrons, and therefore you're adding a little bit of extra energy or pressure because now you've changed the velocity of the thing carrying the pressure change, and so the pressure change is going to have more pressure, and obviously the bigger change is going to take place, so you're going to be adding or subtracting pressure in larger volumes based on how fast you move. And again, the reason why it could possibly matter how fast your very slow hand is moving compared to how fast all this atomic stuff happens, it still must be pretty slow atomic stuff if how fast you move your hand actually can affect how much energy there is. So it sort of indicates that these changes don't happen instantaneously, that it's a work for the conductor to make these changes.
Change of the magnetic field per unit time is stronger. More current. I go out fast. More current. So you see, it's the change of the magnetic field that matters. If I come in very slowly, which I do now, very slowly, you almost see nothing. Right now, the entire magnetic field is inside this loop. The strongest I can have it. Nothing happens because there's no change.
So again, the fact that you can move it slowly and not indicate any pressure changes means that you're changing the pressure so slowly that the meter's not picking it up. But it's happening little tiny bits. You're making real changes, just the changes are happening on a again, so slowly that the meter can't collect enough change to show it to you. The pressure differences are so slow.
Change in the magnetic field. It's only when I do this that you see the current. So an induced current is clearly the result of a driving force. There must be, just like we had with batteries in the past, there must be an EMF. There must be an electric field that is produced in this conducting loop.
So again, he's talking about the field rather than the change. And what's the first change that's happening is you're polarizing the substance. The atoms are either becoming magnetic monopoles or they're becoming magnetic dipoles, depending on the atoms and the circumstance. They could be becoming, in a sense, both.
And so I create now an induced EMF. We used that word EMF earlier for batteries. So now we have an induced EMF, which is the result of this changing magnetic field. And that, therefore, is the induced current times the resistance of that entire closed conductor, whatever is in there. In this case, the total resistance of all these windings, of all the copper wire. That's Ohm's law.
Right, well, that doesn't tell you much. Obviously, it doesn't tell you how much conversion power you're going to have, like how much magnetism you have going in, how much speed you had. It doesn't do any of that stuff. It's just telling you the effect again. No cause in there.
So the induced EMF is always the induced current times the resistance. Faraday did a lot of experiments. And one of the experiments that he did was that he produced a magnetic field. So he ran a current through a loop of some kind. Let's say he ran a current going around, creating therefore a magnetic field. And he was switching the current in and out so that he could change the current. And so it produces a magnetic field. And this magnetic field changes when you close and open the switch. And then here he had his second conducting wire, just like we had there, and he measured in there the current. And what he found experimentally is that the EMF that is generated in here, which I will call EMF generated in my conducting loop number 2, is proportional to the magnetic field change produced by number 1.
Right, so just kind of a recognition that depending on how you arrange these loops, you can capture more or less of the total amount of change in their magnetism. So essentially you're turning the magnetism on and off, you're reversing it in the conductor cable, I mean the first loop, the one you're putting voltage into. And then the second loop, you just want to try to find means to surround that change, that magnetism, and collect as much of that change in the field energy as possible, and to have the most efficiency. And depending on how many loops of wire, then you'll change how much voltage there is, or all these other things. So more loops, higher voltage; fewer loops, lower voltage. Current goes up, current goes down. So again, they're describing the effect, they're not understanding the cause. And the cause is that when you pressurize the wire, until you depressurize it, you can't pressurize it more. So once you've closed the door, you can't close the door again until somebody opens the door. Then you can close it again. So until you put things back to their neutral state or their depressurized state, you can't pressurize them more. You only have so much pushing force. And once you've pushed them, until you let them loose, you can't push them again. And that's the key thing that I think they're missing in all of this.
So the field goes through number 2, and this field is changing. So he noticed that if the change is faster, as you just saw, you get a higher EMF. He also noticed that E2 is proportional to this area, so to the area of number 2. And that gave him the idea that the EMF really is the result of the change of the magnetic flux through this surface.
So again, there's the magnetic flux is just another way of saying the change in the field, and how much of that change, you know, if you're radiating something, you know, the idea would be to capture it. And so the idea is if you're only capturing half of it, then that's all there is. It's always going to be a proportional amount, but the fact is if you want to be highly efficient, you want to capture as much of the change in the field as you can. And clearly in this case, how allowing it to completely depressurize is going to give you more stuff to push. So if you can actually reverse the current, which is essentially switching the battery the opposite way, so you're not going just from north to no north, north to no north, but you actually switch it to south, that means you're opening the door even wider. So now there's even more to push, if you get that, right? So it's just that kind of obvious. So alternating current, it just keeps, you push the door, it flies the door way back open again, so you can push it again, and it flies it open, and you can push it again. You know, it just creates the opportunity to keep pushing, where if the door stays closed, pushing isn't going to do any good. Your change, the change you created in the force, this push, can't be seen because the door is closed. And until you open it, there's no more pushing, no movement.
Of number 2. And I want to refresh your memory on the idea of magnetic flux. We do know, or we remember what electric flux is. And magnetic...
So there's no difference. The electric flux, magnetic flux, it's all one flux. It's just a change in the external environment that you're creating by reflecting things. It's like if I wear a metallic shirt, I will reflect more light. Just a fact. And if for some reason we put a polarizing film over that, or some other gradient, I could reflect more blue light, or I can reflect more of a specific color, more than some other color. I'm changing the environment. And by changing the environment, if I hit something else that's sensitive to those changes, that is, the more I get hit by ultraviolet light, the less ultraviolet light I reflect, like some kind of rule like that, then I am triggered to make changes to the environment. So if I'm opposite somebody who's wearing the same kind of clothes, you know, that changes based on what's hitting it and produces a change in what it produces, reflects, then you could just see that those two surfaces will have to reach some sort of equilibrium in terms of their interaction with each other at some point. And once that equilibrium is achieved, if nothing else changes, if neither one of us hits a button on our shirt to change what's happening, everything just stays static. Something has to, one of the shirts has to be depressurized for there to be any action.
Flux, very similar. If this is a surface, and the local vector perpendicular to the surface is like so, because it could be in a different direction, and the local magnetic field is, for instance, like so, then the magnetic flux through this surface is defined, we call it...
I don't know why the magnetic field's in that direction. I don't know what that direction exactly is. So again, in more confusion, magnetic field what? South, north, magnets in what position. It's just too ambiguous to be a good visualization tool. It doesn't give me much visual knowledge.
Phi of B is the integral over an open surface. This is an open surface of B dot dA. An electric field, we defined in exactly the same way, electric flux, except we had an E here. There was nothing there. So if this magnetic flux is changing, Faraday concluded that then you have an EMF.
So again, it's just all one flux. So there's no electric versus magnetic. They they should always just account for both in any description of a circumstance and acknowledge that as soon as your the increase in pressure always has to be a consequence of a cause, and the two causes are connected. The movement of pressure has to do with first creating it, first causing it, first creating a change. Polarization increases pressure or decreases. The balance of pressure, where the pressure is, that's what it changes. When you convert, when you twist, when I turn this, I change what end is heavy and what end is fat, right? I change what end is black, what end is silver. I change it. And if they all flip, and they all go in that way, you can just see this end is a lot heavier than this end, kind of a thing.
In this conducting wire. So essential is the change of the magnetic flux. If we take some kind of a conducting wire, like so, let's make it in the blackboard for now to make it easy. And I attach to this wire a surface, because the moment that you talk about flux, you must always specify your surface. A flux can only go through a surface. So this is my surface.
So there's no surface. This is a wire. There's no surface. But the surface represents essentially the edge of the wire. There's a proportional relationship between the surface and how much edge there is, or circumference there would be, to that surface, and that's the mathematical reality. The force isn't doing anything by going through the middle of that wire. That force is irrelevant. The only force that's relevant is the force hitting the wire, and it's all hitting it at an angle depending on how you approach it with your magnet. So there's a huge imprecision, because all of this assumes that you're moving your magnet perfectly straight and you have it perfectly centered, and all of that. These are all assumptions built into this mathematics. But the surface is irrelevant. It's just a way of mathematically defining the circumference of the leading edge of the conductor.
Surface now, for simplicity. And there is a magnetic field coming out of the blackboard at me, and it is growing. It is increasing. I will now get an EMF, a current, flowing in this direction. Lenz's law. If the magnetic field is increasing, then the current will be in such a direction that it opposes the change. It doesn't want that magnetic field to increase, and so it goes around like this, the current, so that it produces a magnetic field that is in the blackboard.
So again, just has nothing to do with that. All right, so he's saying he's bringing a magnet from below that's north facing. Again, I have to figure out which way it's going, and then and pressurizing the wire. And as this closed loop sort of indicates, the pressure is really just going to be on one side of the wire. That's the fact of it. And it doesn't move until you provide a place for it to go. So there's no current in the wire until the wire is provided some way to release the pressure. But the pressure is in the wire and in the surface differences. One side of the wire is positive, one side is negative. He's polarized the wire.
So it is the flux change of that magnetic field through this flat surface that determines the EMF. So the EMF is then the flux change d phi dt through that surface. To express Lenz's law that it is always opposing the change of the magnetic flux, we have a minus sign here. That minus sign will never bother you, believe me, because you always know in which direction the EMF is. It's clear that the EMF is going to be in this direction. That's the direction in which it will make the current flow. But we have to put it there to be mathematically correct. That's really Lenz's law. You're looking at Lenz's law here. So you can also write down for this minus the surface integral of B dot dA over that open, I hope you didn't see this, over this open surface. That's the solution. Oops, look what I did. I forgot the ddt in front of the integral sign. Sorry for that. If you put yourself inside that conductor and you march around in the direction of the current, you will see everywhere in the wire an electric field, of course, otherwise there would be no current flowing. And so if you go once around this whole circuit, then that EMF must of course also be E dot dl. Oh.
Well, again, there's no current moving in that wire until you break the wire, okay, to allow for a pressure change to be neutralized. So the pressures in the wire, you have to create some mechanism for that pressure to be altered. And again, if the field keeps moving, well, then the pressure is just back and forth.
Over the closed loop. So you're marching inside the wire, you find everywhere an electric field, and these little sections are dl. E and dl are always in the same direction if you stay in the wire, and so this should be the same, and this is a closed loop. So this is all, if you want, what we call Faraday's law. We never see it in so much detail. I will abbreviate it a little bit on the board there, but I want you to appreciate that there is no battery in this circuit. There is only a change in the magnetic flux through a surface that I have attached to the conducting wire. And then I get an induced EMF, and the induced EMF will produce a current given by Ohm's law. So I want to write down now on that blackboard there Faraday's law in a somewhat abbreviated way, because we have all Maxwell's equations here.
Just say if you take a wire in this circumstance, a closed wire, a wire connected at both ends, and you're moving a magnet in and out, you can sort of understand that to the wire the pressure is just going this way. There is no movement to the pressure. And when you break the wire, one side of the wire is going to say, I'm high pressure. The outside of the wire is going to win, let's say, and it starts letting high pressure out. Then the other side's automatically going to go low pressure, because that's going to be the migration. So as soon as you cut the wire, you create a positive and a negative end. And the rule is that it tends to do this right-hand thing. Okay, that's the rule, that what side becomes positive and what side becomes negative in terms of allowing the pressure out is based on a rule that just has to do with how water spins in a toilet. I mean, there's a rule that's based on some element in the mechanics. If I think about it, maybe I can figure that out, what it would be, why there's such a rule. But there is such a rule. One side goes positive, one side goes negative. There's a rule. But there's no current moving until I allow there to be this pressure change. That is where I allow the high pressure to get back into the low pressure area, and I allow the high pressure to get out so it can depressurize. So I have three pressure. So when I cut the wire, there's a 3 pressure layer over here, and there's a 5 pressure layer over here, and vice versa. One of them wins on the right hand versus left hand side, up, down, whatever way it's turning. And so one side becomes the 5 and one side becomes the 3, and all you're doing is re-equalizing them again through the wire. And then you have what you could call a transfer of the pressure, a movement through the wire. But there's no current until you allow the pressure to be neutralized.
And so we now have that the closed loop integral, closed loop of E dot dl, that's that induced EMF. You could take minus d phi dt, or the time derivative of the integral B dot dA. That's the one I will take. Integral of B dot dA, and this is over an open surface. And that open surface has to be attached to this loop. And that is Faraday. We have Gauss' law. We have Ampere's law. We have this one, which tells you that magnetic monopoles don't exist. This would only not be zero if you had a magnetic monopole and put it in a closed surface. Come and see me if you find one.
So again, yes, it's in my opinion quite obviously there's lots of them. The electron and proton are the most elemental monopoles, but clearly atoms can become monopoles when they're pressurized or depressurized also. And then of course bigger things can be monopoles. You can charge a surface and it's a monopole.
And this now is Faraday's law. So you think that all four Maxwell's equations are now complete? Not quite. We're going to change this one shortly. So we can't celebrate yet. We have to wait. It's a big party.
So you'll notice people who say that Maxwell's equations are about waves. There's no waves in any of this. There's no, you know, to any substantial part. Now a little bit of frequency will get gotten into once you start, you know, doing the on-off thing. Now you're creating frequency, and now you have some sort of waves, but very minor. And again, the waves are really can be understood as you're turning something on and off. It's not exactly a wooey kind of wave. It's kind of an obviously caused wave. It's a very binary cause.
There's always a little bit of an issue about the direction of dA, and I will explain to you how the convention goes, but it really is not so crucial because Lenz's law always helps you to find the direction of the EMF. But if we are trying to be purist, if this is my conducting loop, and if I attach a flat surface to this, if I did that, and if I go around closed loop integral E dot dl, Faraday doesn't tell me which way I have to go. I can go clockwise, I can go counterclockwise. We will then do the same thing that we did before with Ampere's law, apply the right hand corkscrew rule, and that is that if you march around clockwise, then dA will be in the blackboard, perpendicular to the blackboard, perpendicular to the surface, and if you go counterclockwise, then dA will come towards you. The surface doesn't have to be flat. It can be flat, there's nothing wrong with it, but there can also be a bag attached to it.
Alright, so this is sort of, I don't know what exact use that would be. I guess there's in some context that would make some sort of sense. But again, this all has to do with using this area argument as an argument for how much of the surface of this wire will come in contact with force. So there's a proportional relationship between this area and the amount of wire surface, the circumference. So that's kind of obvious. That's just the pi kind of stuff, and any kind of, you can average any shaped surface into a circle, you know, its volume into a circle. So you get the area, you average it into a circle, and then you know how much exposure there was to the wire. And making the bigger surface just says we're going to extend the amount of time you're exposing this wire to the effect. So the bag just has to do with how much you're going over, you're changing how much distance you're exposed to, how much you're adding a kind of a time component.
As we also had earlier, I have here close conducting wire, And I could put a surface right here, but I can also make it ahead, like this, perfectly fine. Nothing wrong with that. That's an open surface attached to this loop. That's fine. You have a choice. And the convention with dA is then exactly the same, but if you go clockwise, then the dA would be in this direction, using the right-hand corkscrew.
So again, now you'd just be calculating how much wire went through the surface. So you're just adding more iterations of exposure by doing the bag thing.
Locally here, if you went counterclockwise,
and then you just average those out again to figure out what your at any one your Planck amount of exposure.
The dA would flip over. So what is now the recipe that you have to follow? You have a circuit, electric circuit, that determines then your loops, of course. You can take loops anywhere in space, but that's not too meaningful. So you take them into your circuits. And so you define the loop first. Then you define the direction in which you want to march around that circuit. You attach an open surface to that closed loop. And you can determine on that entire surface the integral of B dot dA. Everywhere on that surface, locally you know the dA, locally you know the B, you do the integration and you get your magnetic flux. And then if you know the time change of that magnetic flux, then you know the EMF. If you go...
So again, it just has to do with the exposure to the edge of the wire is going to be completely proportional to the circumference of that wire, to the length of it. And you can determine the length of it by understanding the area it encloses. Those two, the area will tell you that circumference.
Go around in this conducting circuit and you measure everywhere the electric field, then the integral of E dot dL, if you go around the loop, will give you the same answer. And that connects the two. The magnetic flux change is connected with the integral of E dot dL when you go around.
Obviously, if all these undulations or changes in its form, some parts will be closer to the magnet, some parts further. So you're just basically arguing that those will average out to some amount.
You have to take that minus sign into account. How come it doesn't matter whether you choose a flat surface or whether you choose a bag? Well, think of magnetic field lines as a flow of water or spaghetti, if you like that, or a flow of air. It is clear that if there is some kind of a flow of air through this opening, then it doesn't come out somewhere, so it always comes out of this surface. And therefore, you're really free to choose that surface. But
so again, I think it's just a terrible analogy, because what you're really measuring is how much flow went by the wire. That's it. The only thing getting affected is the wire. The wire is not sensing what went inside of the loop. That's not what the wire can do. The wire can't see how many fish went through into the bag. It's just counting the fish that hit it. And it's just because there's a proportional relationship between how many fish are going through and how many are going to hit you. That's just a fact. So if you can measure how many fish went into the bag, you'll know how many fish hit the wire that's around the bag, because the two are perfectly related.
you always pick a surface that is the best one for you. Now all this looks very complicated, but in practice it really isn't, because your loop is always a conducting wire in your circuit, and the minus sign is never an issue because you always know with Lenz's law in which direction the EMF is. In fact, when I solve these problems, I don't even look at the minus sign. I ignore it completely. I calculate the magnetic flux change, and then I always know in which direction the current is, so I don't even look at the minus sign.
So again, there is no current until you allow it to, until you allow there to be a pressure change. So until you open the door, you can't close the door, and it's just fact. Anyway, so I think that's probably enough for this video, and thank you for your attention, and we will continue soon and such.